Newton's laws, 2D motion and vectors. So in the second law, F equals ma, where F is the resultant force and a is the acceleration, if we're given vectors, so in column vector form or component ij form, we use this version of the formula, and when you're writing this, underline the F and the A because they're vectors. Example 1. A mass of a half a kilogram has a resultant force of 3I plus 8J acting on it. We need to work out the magnitude of this resultant force. So that's basic Pythagoras' theorem. Okay, so we've got 3 to the right and 8 up. Pythagoras' theorem, and we're looking for the magnitude of the force, so use this notation. So 8.54 newtons. So the diagram in vector form is like this. So along here we have a force of 3I newtons, and then along here we have a force of 8J newtons. The resultant force is 8.54 newtons, that's the magnitude, and its direction is given by this red arrow. So we have the size or magnitude of every force, 3 newtons, 8 newtons, 8.54 newtons, and the direction of each force given by these arrows. The acceleration will be in the same direction as the resultant force. So to calculate acceleration, and acceleration will be a vector, we're dealing with vectors, so F equals ma, resultant force equals our mass times the acceleration. So underline your vectors and then solve, and then if we want the magnitude of the acceleration using Pythagoras' theorem, 17.1 meters per second squared. Part C, we want the direction of the acceleration as a bearing. So this is the vector for acceleration, and here's the magnitude. We've calculated this already. And then from the diagram here, right angle triangle, so we have angle theta here. So tan theta will be opposite over adjacent, 16 over 6. So theta is 69.44 degrees. And then to work out a bearing, an angle measured clockwise from north, this is for our resultant force. So we're looking for angle alpha, so 90 minus this angle theta here. So alpha, or our bearing, is 020.6 degrees, given as a bearing. And the magnitude of the acceleration was 17.1 meters per second squared. So we have acceleration in vector form, 6I plus 16J, and then we have the magnitude of the acceleration, and the arrow is giving the direction along here for our acceleration. So magnitude and direction for acceleration. Example 2, we have 3 forces which are acting on a body of mass 60 kilograms, and the acceleration produced is given here, and these are all in vector form. So, and we're using vectors in 2 dimensions here. We have 2 unknowns, P here and Q. Now we can connect all of these together using F equals ma in vector notation, so like this, and I've added all of the forces together. So the x component for the forces, so we've got 80 plus the minus 75, so that's 5 so far, plus 10p, there we go. And the y component, so we've got 50 plus the 100, that's 150, plus 20q, here we go. So resultant force equals mass there times the acceleration. So I've done some multiplication here. We've multiplied the vector here with this scalar quantity, so 60 times 0.8 gives 48, 60 times minus 1.5 gives minus 90. So the x component, so 5 plus 10p, is equal to the x component here, 48. We solve to get p. And then the y component here is equal to the y component here, So we can write this equation down, solve to get q. For practice, try these questions.